Okay, so today what we're looking at is our first POE screencast, which is Introduction to Structural Member Properties. And so what we're going to work through is moment of inertia, modulus of elasticity, and beam deflection. So moment of inertia is a mathematical property of a cross-section that gives important information about how that cross-sectional area is distributed about a centroidal axis. Now, what a centroidal axis is basically the center point of any object. So you may be familiar with center of gravity in physics or science class. So you'll have the same amount of material on both sides of a centroidal axis. So it's the stiffness of an object related to its shape. So here I have a diving board. You'll notice that it has a long rectangular shape. People dive off of that and get a spring enabling them to go higher up in the air before they enter the water. The platform has a square shape. So people just push off of that in order to enter the water and get a good start for a swimming race. So two different things going on here. This is going to flex a lot due to its shape, and the platform is not going to flex very much. So the platform has a higher moment of inertia than the diving board. It says, in general, higher moment of inertia produces greater resistance to deformation. So we have two boards here. We have a joist that's positioned upright, and we have a plank that's positioned horizontally. Everything else is the same. Length, width, height, and therefore area and material is all the same. So what makes the difference in moment of inertia? What distinguishes beam A from beam B? Well, it's going to be the orientation, as we'll see here in just a minute. So, will beam A or beam B have a greater resistance to bending if an identical load is applied to both beams at the same location? Think about your house. You have beam B, which is more like floor planks. If you have a hardwood floor, you can see this very easily. Whereas A is the joists. So if you go down to your basement, if you have an unfinished basement, you can see the joists and their vertical orientation. And then the planks are on top with their horizontal orientation. So beam B is going to have a greater resistance to bending than beam A. All right, so why did beam B have a greater deformation than beam A? Well, it has to do again with the orientation. So you have a very different moment of inertia, as we'll see. So we're mainly going to be dealing with rectangles here for our moment of inertia. So our formula is I equals base times height cubed divided by 12. So if I look at both of the beams, if I calculate the first one, you're going to have a base of 1.5 and a height of 5.5 inches. So I'm going to cube the 5.5 inches first, and notice how I get a very large number of 166.375 inches cubed. Multiply that by the 1.5 and you get 249.5625 inches to the fourth. And that's divided by 12. So an overall moment of inertia of 21 inches to the fourth. Whereas beam B, now if I turn it on the side, only has a height of 1.5 inches, where the base becomes 5.5 inches. So if I cube 1.5, I only get 3.375 inches cubed, a lot less than I had with beam A. So I work the problem all the way through, and I get 1.5 inches to the fourth. So beam B has a much lower moment of inertia, therefore much more flex than beam A. 14 times stiffer. So this is why you want joists to support planks and not the other way around. So why do we use, though, composite shapes? We don't always use just a flat beam or a rectangular beam. We cut notches out of some of them. So really it has to do with economics here, is that you can do more with less. You can have a similar moment of inertia for an I-beam as you can with a rectangular beam. Now notice the area here, 10 square inches, also 10 square inches with the I-beam, but you have 23.8 square inches with the rectangular beam. Doesn't seem like that much, but when you're using lots and lots of beams to build a structure, that difference adds up quickly. So you're not really sacrificing that much stiffness with an I-beam versus a rectangular beam. 178 versus 130, but down here you have 13.3 inches to the fourth. Okay, so what about chemical makeup? What happens when stuff is made out of different materials? This is called the modulus of elasticity. It's the ratio of some specified form of stress to a specified form of strain. Basically, it's putting all other things equal except the material. So here we have a spring diving board that's made out of some sort of composite material and has a steel back to it versus a platform diving board, which is concrete. So we know that the spring diving board flexes a lot more than the platform diving board. So we can tell that concrete is stiffer and has a greater modulus of elasticity than the spring diving board. So in general, higher modulus of elasticity produces a greater resistance to deformation. So if I take A, which is Douglas fir, and I take B, which is ABS plastic, which one is going to have a greater modulus of elasticity? Everything else stays the same, therefore these two beams have the same moment of inertia. So what distinguishes beam A from beam B? Well, of course, it's the material. So which one will have a greater resistance to bending? The plastic or the wood, if the same load is applied? Okay, the plastic is going to have a greater bending force, therefore a lower modulus of elasticity than the wood. So why did beam B have a greater deformation? Well, again, has to do with the material, difference in their elasticity. Okay, so that we call that delta max. All right, so we have an applied force or load, length of a span, modulus of elasticity, and then a moment of inertia. All right, so here's how we calculate the deflection of a beam. Delta max equals force times length cubed divided by 48 times modulus of elasticity times moment of inertia. So if you notice here, the Douglas fir, 1.8 million psi versus the plastic, 419,000 psi. So if I calculate it for beam A, I'm going to take all of my variables and plug them into my beam deflection equation. 250 pound-feet times 96 inches cubed divided by 48,000, 1.8 psi times 20.8 inches to the fourth. So I get only 0.12 inches of beam deflection. Now, that's going to vary depending on your load. Whereas for beam B, notice how I have a lot less of E, so I should get a lot more